Hey guys, this is Monica, and today for problem 1 part A, we want to explain how the specific heat at constant volume and the specific heat at constant pressure relate to the gas constant R. So here we are comparing these two paths. The first path, path A, corresponds to this Q here where we have the constant volume. So we have Q equal to N times C at constant volume times delta T. And this path B here corresponds to this one here where we have constant pressure and Q is equal to N equal to Cp times delta T. So for path A and path B, we see a change in temperature. So we start from this isothermic graph to the second isothermic graph, and we see the change of temperature from initial to final in path A, and we see the path for B from initial to final. And since the two final points both end on this second graph, we know that they will have the same final temperature, so the change in temperature for path A and path B will be the same. Now, for the thermal energy, we know that the delta E is not path dependent, so if we have the same temperature, this automatically means that we're going to have the same delta thermal energy. So for the change in thermal energy for process A, we have work plus the specific heat. And so for process A here, it's the one where we have constant volume. So we don't have any area under the curve, so we don't have any work being done by the system. And Q is simply the specific heat when we have constant volume. Now for the second path, the change in thermal energy B, same thing, we have W plus Q, but in this case we do have some area under the curve, which is the pressure times our change in volume plus our Q when we have constant pressure. Now what we do is we equal the thermal energy for path A equal to the thermal energy for path B, and this is the expression that we have here. And now the next thing that we want to do is relate this delta V to the delta T's in the expression, and we do that through the ideal gas law. So since this expression came from the path B, we want to relate the ideal gas law to this part of the problem. So for path B, we know that our pressure is constant, so there's going to be no change in pressure, but we do see a change in volume. N and R are also constant, and we do have some change in temperature. So next what we do is that we substitute this NR delta T for the P delta V in the original expression. We plug that in and we factor out the N delta T so that we have CV equal to negative R plus CP, and just to rearrange this we get the equation 19.31 in the book, which is CP equal to CV plus R. Now for the second part of this problem, we are asked to explain why it is that equation 19.32 in the book, which is this, the specific heat, is equal to NCV delta T. And as we can see, this right here is the same expression for the specific heat when we have constant volume. And we are basically asked to explain why it is that these two relations don't contradict each other. And the reason they don't contradict each other is because we want to ask ourselves, what is it that we are calculating? If all we want to calculate is the thermal energy, it doesn't matter which one we choose, because the thermal energy for path A is essentially just equal to Q, and for path B it's W plus Q. But since E delta E is not dependent on the path, we can simply just use this one and save the extra step of adding the work to it as well. But if we want to calculate Q, this is path dependent, so it does matter which one that we use. So you want to pay attention if the system, it has constant volume or constant pressure.